Good morning, guys.
Good morning, sir.
So why only few people, man, around 12, 13?
So I think webinar is going on.
Okay,
I'm not sure, but I think.
okay. Is Chandan there? Chandan?
No, sir. I think he is also in that webinar.
Acha. So how many of you are attending it? 14 in the sense restaurant.
Yes, sir.
Okay.
So they will come again. Meeting is over.
They will?
So they will come, sir.
Okay. So we should wait for some time.
Okay, sir.
Yeah. Okay. Shall we start?
Yes, sir.
Okay. So R of conduction is L divided by Ka. R for convection, resistance for convection is 1 divided by Ha. And what is R for radiation?
One divided by F into sigma A into
Hmm.
T1 plus T2 divided by T1 square minus T2 square. T1 plus T2 square.
Okay. So these are the resistance values for the three modes of the conduction, is it? Okay. Now, let us try to analyze in this way. What is K here? First of all, let us compare two things and later we shall look into the radiation. Now we shall look into only the conduction and convection comparison. Okay, so this is important to understand. What do you mean by universal heat transfer coefficient or overall heat transfer coefficient? What does it exactly mean that you have to understand? Coefficient. Okay. Now, what is K?
Thermal
So K
conductivity.
is nothing but thermal conductivity, okay, which defines the ability of the material to conduct. Keep the sentences. Understand the depth of the sentence is very important. What does K define? K defines the ability of the material to conduct. What is H then? What is H?
Heat transfer coefficient.
Heat transfer coefficient. So, as K describes the ability of the material to conduct. Similarly, H, that is heat transfer coefficient, defines the ability of the material to convect. I mean to say, how best it could offer the convection within itself. So that ability of the body to convect, that means to conduct a convection heat transfer, is given by the value of H. Okay. K describes the ability of the material to conduct, and H describes the ability of the material to convect. So, what are the units of H then? H is equal to watt per meter. What are the units of H?
Meter square per degree
Meter
Celsius.
square.
It is meter square Kelvin or watt per meter square degree Celsius. Either of the things are there, depending upon the temperature of measurement. Now, coming to this concept, I want everyone to be interactive and attentive, even, okay? Because this is important. If you understand this, then the concepts and the problems all are going to be damn easy, okay? Just understand this. Now, there is a slab or a material like this, section of a material. This is at a temperature T1 is equals to 100. This is at a temperature T2 is equals to 50. And I define K of this material to be 10 watt per meter Kelvin. So let us assume both of these are in Kelvin. Now, I want to calculate what is the amount of heat transfer. What is the amount of heat transfer that is transferring from this to this? So what is the amount of kev that is transferring from section A to section B? Okay. So how do I calculate it? I want the value of kev in this case. How do I calculate it? Go with the analysis. If you forgot, if you're in a position not to understand, if you don't remember anything regarding heat transfer, working time, just let me check. Okay, so today's half fine. So kev, the value of kev, if you do not remember to analyze or anywhere in the heat transfer, go with the electrical analogy.
Con-
What does an electrical analogy says? V is equals to, sorry, I is equals to V by R. So I is the amount of current that you want to flow within the system, and V is the potential difference across its ends like this that is driving the current, and R is the resistance which is offered to the flow of current. So same analogy I want you to be carried out in this particular case. I want everyone to understand this. This is very, very important. If you understand this, your whole of heat transfer is easy. Same electrical analogy here. In place of current, I have heat. That's it. So what should I do? How do I calculate?
Heat transfer into area.
Wait. I want just you to apply the electrical analogy. So analogy in the sense, this is the electrical concept. The same concept I want you to apply in the heat transfer. Okay. Now, here the flow of charges is known as current. Here I want the flow of heat. That is your heat conducted value. Correct.
Yes.
Here there is a potential difference between the ends, but here what is there?
Temperature.
That's it. So I want, first I'll take the temperature difference now. Here there is an electrical resistance that offer resistance to the flow of charge. Similarly here, there should be some thermal resistance that offer the restriction to the flow of heat. And at that particular thing, can I take it as our conduction here? Yes.
Yes, sir.
Yes, sir.
So, substituting further, Q is equals to T1 minus of T2 divided by L divided by Ka. Why L by Ka? Because it is conduction. So, the resistance value in case of a conduction is L divided by Ka. If you transfer Ka to the numerator, it would be Ka. Difference in the temperature is nothing but Tt divided by L is nothing but your change in the length, that is Tx. It is nothing but which law? Which law is this?
Fourier's law.
Exactly. So it is Fourier's law of heat transfer. So this governs which principle? It governs the conduction mode of heat transfer, and that is how it is. So you can similarly go with all the other things. Okay. Let me come back to this. It was just a recap of the previous sessions. Now, what happened? Now I have explained you how to use of electrical energy in order to solve the problems on the heat conduction, where Q is given by change in temperature divided by resistance to the of that particular thing. Suppose now, for the same slab, I add one more material like this. Okay, this is of a different material, and this is of a different material here. Okay, so this is having a length of L1, and this is having a length of L2. Okay, okay. So this having a thermal conductivity value of K1, and this is having a thermal conductivity value of K2. The temperature here is, wait a minute. The temperature here is T1, which is 100. The temperature here is T2, which is 25, sorry, 50. And the temperature here, we shall assume it as somewhere around 25. Okay, so this is the scenario now. I want, let me name these labs before we get into it. So this is slab 1. Okay, let me write here. And this is the slab 2. Okay, now I want what is the heat that is getting transferred, the heat getting transferred from this point until this point. What is the amount of KIF that is getting transferred from this point here to this point? Okay, how do I do it? Hmm. How do I do it?
First, we apply the electrical energy to the first lab.
Okay, first we shall apply the electrical energy for the first lab. Okay,
After that,
then
uh, compare the temperature difference between T1 and T2 is taken, and that answer is compared with T3.
okay. So what if, okay, Karthik, your and Rakshan's answer might be correct. Okay, I'm not saying it as wrong, but I will try to apply from this point to this point, treating this as a whole slab now. Okay,
Okay.
so let's check that. Now, see, what should be my temperature difference here? Whether it should be T1 minus T2 or it should be T1 minus T3. I'm considering from this point to this point.
T1 minus T3.
So it is T1, sorry, it's T1 minus T3 here. That's right. Now, even here it also, I should consider the resistance. Now, I will be terming it as the overall resistance. Okay, the resistance overall, or even I can call in the simple sense R net, the net resistance. Okay, this net resistance is composed of resistance due to conduction offered by first slab plus resistance due to conduction which is offered by the second slab. Am I right?
Yes, sir.
Okay. So how do I calculate resistance offered due to conduction with respect to the first slab? So generally our conduction, resistance offered in the conduction is given by L by Ka, applying it to the first slab.
Length of the first slab divided by
Length of the first slab in the sense L1 divided by
resistance offered by the first lab.
resistance. What is
K1.
K? What is K? Is that resistance fraction? It is Thermal conductivity.
Thermal conductivity. Thermal conductivity.
So it is K1 into A. Okay, why? Because the area of cross section, if you measure this, the area of cross section of both the things would be same, right? So there is a common
Yes,
area
sir.
of cross section. Sometimes your area of cross section should also differ, and we shall teach in the further classes how to deal with such problems. Now, as of now, the area of cross section is same for both the slabs. Next, and this is for the resistance offered by the first slab. Now, I want you to answer what is the resistance offered by the second slab.
L2 divided by K2 divided.
L2 divided by K2 into A. So this is R net, right? So
Yes,
if
sir.
I want to calculate the value of K, that would be what? T1 minus T3 divided by L divided by K1A plus L2 divided by K2A, right?
Yes, sir.
No. Okay. Continuing further. And this is important. See, I am trying you to make use of different forms of heat transfer and try to analyze at a single instant. Okay. Now, there is a plane wall here. Okay. In this plane wall, at the either side, there is a cold fluid which is flowing. The cold fluid which is flowing. Now, I say the wall is at the higher temperature. I can take it as Ts, which is the surface temperature, which is at the highest, say around 250 degree Kelvin. And the point at which the air enters, the fluid temperature initially would be around, say, normal room temperature, 28 degrees Celsius. So it is in Kelvin, it is around okay, just a minute. Let me take both the things in degrees Celsius before we start. So this is in degrees Celsius, and here it is around 28 degrees Celsius here. Okay, now the heat is getting transferred from the surface to the flowing fluid here. So which type of heat transfer is this? Which type of heat transfer?
Convection.
Convection. So in this case, this is the temperature curve which I am drawing. The temperature here gets increased when it reaches here, correct? And this is because
Yes.
of convection. Okay. Now, in this case, if I want to analyze what is the heat transfer, what is the heat transfer? So how do I analyze? So where is Kev? Kev is equals to temperature difference. That is, yes, I want you to answer now. How do I analyze Kev for this? I want to calculate the heat flow.
Temperature of the fluid minus temperature of the surface.
Surface temperature is the higher side, so it's better to take Ts minus Tf, okay, divided by which resistance I am supposed to calculate here.
Convection. Resistance offered by
And the resistance offered by the convection, so it is R convection here. So what is R convection?
H divided with
It is
1.
H1 divided
1.
by HA. So Q is equals to Ts minus Tf divided by HA, 1 divided by HA. If you transfer HA to the other side, numerator, it would be HA into Ts minus Tf. If you look back to your notes, this is nothing but which law? It is which law?
Newton's law of coolings.
It is Newton's law of cooling. Okay, that is how it is interconnected. So this is the convection offered resistance. Now, the other two men. Now what I'll be doing, you just observe, this is very important. Okay, I take a wall like this. Okay, there is a fluid flowing in this wall like this, and there is another fluid flowing outside the wall like this. Okay, the initial, I will just mark the temperature lines here. I mean to say, the initial temperature is T1 here. When it reaches the wall temperature is T2, and the inner wall temperature is T3, and here the temperature is T4. Got it? And this particular material here has a thermal conductivity value of K, and it has a length of L1. Okay. For the transfer of heat from the first fluid to the T2 segment, I will take it as H1. So H1 is the governing thing, and the transfer of heat, the amount of heat that is getting transferred from the other fluid on the face of T3, I would take it as H2. Now, I say the temperature is increased from T1 to T4. I want you to calculate what is the amount of heat that is getting transferred from T1 to T3. Getting my point? I want you to calculate what is the amount of heat that is getting transferred whole from T1 to T3 in a single shot. How do you do it? So K is equals to
Sir, is that T1 to T3 or T1 to T4?
T1 to
T3 or T1 to T4?
T1 to, sorry, T1 to T4, the whole thing,
Thanks.
the transfer of heat from T1 to T4. How?
Can be divided in three different parts. First for H1, then K, and then H2.
What you are dividing, Ashwita?
Uh, I thought I'll take three of them separately and then add them for Q.
Okay, fine. So you're talking about the resistance, I hope. So we will calculate R net. So the temperature difference between these two sections is what? T4 minus T1, right?
Yes.
Electrical energy has been done. So if I somehow manage to calculate what is the total resistance offered for the flow from T1 to T4, what is the total resistance offered from T1 to T4 to the flow of heat, I can calculate what is overall heat that is getting transferred from T1 to T4. Yes. If I calculate the overall resistance, I will be in a position to calculate the overall heat flow. Yes or no?
Yes, sir.
Correct? So in this case, I must calculate what is the overall resistance that is being offered. So resistance is being offered initially from T1 to C. The resistance is being offered initially from T1 to T2. So which resistance here has been offered? Which type of resistance?
Convection.
Very good. So it is convection here, and the resistance which is offered from T2 to T3 is what?
Conduction.
Conduction.
Conduction. Very good. So and the resistance offered from T3 to T4 is again
Convection.
Convection.
again the convection. Now, same thing. If I want the R net value, I'm supposed to add all this, right?
Yes,
Resistance
sir.
due to convection in the first segment, that is T1 to T2. Can I take it as 1 divided by H1 into A
Yes, sir.
plus what is the resistance offered due to conduction
L divided by
from
K.
T2 to T2? L1 divided by Ka plus what is the resistance offered due to convection from T2 to T3?
1 divided by H2 into A.
1 divided by H2 into A. So this is my overall resistance which is offered. So if I want to calculate the value of Q, it is just T4 minus T1 divided by 1 divided by H1A plus L1 divided by Ka plus 1 divided by H2A. Clear with these concepts? Understood?
Yes, sir.
And the last part, guys. This is the last part. If you understand this, the whole lump sum is easy. Okay. Now I will take three blocks, each having the thermal conductivity values of K2, K2, K3, and K1. Here the fluid is flowing, and here the fluid is flowing, which has the heat transfer coefficients of H1 and H2 respectively. The lengths of this is L1, L2, and L3 respectively. And the temperature, which is initial of the fluid temperature here it is T1. The wall temperature is T2. Here it is T3 at the junction, T4 at this junction, T5 at this other surface. T6 is the temperature of the other fluid now. So these many junctions are there. Okay. In this, I want to calculate the value of Kf. Yes, I'm supposed to do it.
T6 minus T1 divided by resistance offered by the 5 sections.
T6 minus T1 divided by R
R
net.
net.
And this R net, can I write it directly? First one is R due to convection. If it is due to convection, it is 1 divided by H1 into A plus. Next, T2 to T3 is nothing but your conduction. So resistance offered by the conduction is K1 divided by L1
L1,
into A.
sir. L1 divided by K1.
Okay, L1 divided by K1 into A. Yes, you're right. So L1 divided by L1 divided by K1 into A plus the resistance offered by this particular slab here, okay, for temperature transfer from T3 to T4, it is L2 divided by K2 into A. Similarly, for the third slab, it is L3 divided by K3 into A. And last, there is again a convective heat transfer from the T5 surface to the T6 fluid. And how am I supposed to calculate that particular resistance?
1 by H2
1 divided
A
by H2 into
H2A.
A. So if you suppose to calculate, if you manage to calculate what is the resistance offered, then easily you can calculate what is the heat transfer from this particular point to this particular point. The how much amount of heat is being transferred, you can calculate by this particular analogy. Okay, understood.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
okay. So these are very important concepts what we have discussed today. If you learn these concepts, your problems are damn easy. Okay, that I can assure that. Okay, there is one bit of derivation, and there are something known as boundary conditions of first kind, second kind, and third kind. Those will be discussed in the next week. Okay, so tomorrow is Sunday. Enjoy your Sunday, guys. I will take the attendance anyhow. So, any plans for tomorrow? Sunday plans?
Sleeping, sir.
Sleeping. Okay. So, I have a plan to go to that. Some of our faculties are organizing a trek near that Etina Puja. How is the place, man? Etina Puja or something. It's good.
Don't know, sir.
So go to
Don't know.
Konaje Kullu. Konaje Kullu is good.
Konadikallu, I have visited around 7 to 8 times. I used to,
Good.
and that's a great place. And out of all those 7 to 8, just will stop recording. Why all these should be recorded? Mm.